So hello everyone, we are back to our plasma class, and in this class we will be studying the Paschen breakdown criteria, which we already started in our previous class, that there is a cathode and there is an anode, and in between that there is a gap D, and some electrons are emitted from the cathode and they are moving under the influence of electric field towards the anode, and on the way they are colliding with the other charged particles and causing ionization. So while doing so, they are exciting other particles and they are making them to emit photons, and those photons are causing further ionization, photoionization. Then they are also participating in the ionization phenomena. So ultimately, the total number of electrons what we are getting at the end of your discharge tube is n equal to n0 exponential alpha d plus np. And what are the different parameters that we have explained, and that is written on the upper right corner of this slide. So this discharge gap n0 is the number of electrons that has been emitted by the cathode. Np is the total number of photoelectrons reaching the anode. N Townsend is the total number of electrons generated through Townsend mechanism, and N is equal to Np plus N Townsend. So that gives you the total number of electrons that are finally reaching the anode. So in doing so, we want to make a derivation when the number of electrons which are reaching to the anode will be infinite, because that will correspond to the breakdown of the gas that we have filled within the plasma tube. Now let us consider a very small elementary length dy in the gas, some distance y away from the anode. Okay. So suppose some intensity now falling on this dy length, and that intensity will definitely get reduced because of the absorption, and it will be coming to I dash when it is coming out from that elementary length. Now the decrease in the intensity, that is you can calculate as di, that equal to, if I equal to I0 exponential minus mu y, so which is usually the typical relationship of intensity as a function of distance when absorptions are occurring. So if y is the distance it travels, then it gets reduced to I equal to I0 exponential minus mu y. Mu is the absorption coefficient. Now what happened, this di, if you make from here, then it becomes I0 minus mu into exponential minus mu y into dy. So this is the kind of relationship it bears with the this small length of the gas of say dimension dy. So di is basically is proportional to I0, and I0 this is proportional to the total number of electrons which are reaching the anode. This is because I0 is the intensity of light that is getting generated because of the excitation of the atoms inside the discharge tube, and that will be proportional to the total number of electrons that has been generated, and we have taken C as constant of proportionality. So I0 is equal to C into N. Okay. So what we are getting now, this di is equal to I0, we have replaced that with Cn just from this logic, and then we have put this minus mu over here, then exponential minus mu y and dy. So what you are getting now, the number of electrons that has been generated due to this photoabsorption, that will be proportional to the amount of intensity that has been reduced within this elementary length. So that is di is equal to Cn minus mu exponential minus mu y into dy. So this will be proportional to this di, and di is having this functional relationship, and if you absorb rest of the constant within this another constant f, so c, mu, all these are absorbed here, and what is remaining n, and then exponential minus mu y dy. So the number of photoelectrons which has been generated out of this, that is equal to f n exponential minus mu y dy. So these are the electrons which will now participate in the Townsend breakdown mechanism. In the similar way, as the electrons which are emitted by the cathode, and they are moving and they are causing the ionization. Now these photoelectrons which are generated within this elementary length of the gas dy, they are this much in number dne, and these electrons which are produced here, they will now move as per the electric field towards the anode, and they will produce the number of electrons through your Townsend mechanism like this one. So this is the dne and dne exponential alpha y. So if you now absorb the the rest of the coefficient, as I told you that it is in f, then what is coming here, this f n exponential alpha, this alpha is coming here, and then alpha minus mu, then you are getting this y is getting taken common outside, and then dy. So total number of electrons which will be produced because of such photoabsorption, if you want to calculate that, then you have to integrate from this your y equal to 0 to d. So that will be the length scale. And if you do that integration, then total number of photoelectrons which are coming here, that equal to n, this f dash by alpha minus mu exponential alpha minus mu d minus 1. How it is? So if you integrate this, then this alpha minus mu will be coming down, and then this will be integrated over this 0 to d. So once d will come here, and then next time you will put 0. So it is like that. Now what is there? N f, then alpha minus mu at the bottom, and then exponential alpha minus mu d minus 1. So total number of photoelectrons will be this one. Okay. So here from you are coming over here, and then you are integrating this, and you are getting this value for the number of photoelectrons generated. Now if we go back, then n total number of electrons that will be reaching the end of the discharge gap will be n equal to, this is the Townsend mechanism, and this is the number of photoelectrons generated. And we have just now calculated what is the number of photoelectrons generated using this mechanism. So total number of electrons that will be reaching the end of the gap is n equal to n0 exponential alpha d plus n into f dash by alpha minus mu exponential alpha minus mu d minus 1. Okay. So what I am now getting, that n, you see that it is on the left hand side as well as on the right hand side. So you can take n common, and then f dash by alpha minus mu, you name it as gamma, and then gamma is appearing over here, and if you take n this side, so 1 minus gamma exponential alpha minus d minus 1 is coming there, and you just divide n0 exponential alpha d divide by that quantity, this one, then you get the total number of electrons that will be reaching the anode finally. So including your Townsend mechanism as well as including the photoelectrons followed by the Townsend mechanism. So now what do you want actually? This is the total number of electrons which are reaching the anode, and for breakdown we want n to be infinite. Okay. So at this point we will make some approximation that to make n infinite, we need this denominator to be infinite, 0 actually. So something divided by 0 will be infinite, and in doing so, what help we are taking? We are taking the help of your the Townsend mechanism through alpha, and the photo absorption mechanism through mu. Now there are two conditions for n to be infinite. So one thing is that we can straight away make this denominator 0 and make this infinite. So that is your necessary condition. But suppose we are not taking the help of the absorption of the photons, they are only helping you to get the breakdown happen in an easier way. So if we don't take help of this absorption and still find the condition for n to be infinite, so that will be the sufficient condition. So for the time being, we can put this mu is equal to 0 over here, and then we will try to find out this quantity to be 0. So if we are putting mu equal to 0, that means that we are not taking the help of this absorption, and still we are trying to make this quantity infinite n. Okay. So that will be the sufficient condition, but don't forget that this mu is already there in this gamma, this f dash by alpha minus mu. So we are not completely eliminating the effect of the your absorption, but in the exponential term we are just not considering the effect of mu, the absorption. So that will just give us the sufficient condition for the number of electrons reaching the anode to be infinite. So we put mu equal to 0 and make this denominator 1 minus gamma exponential alpha d minus 1 equal to 0. So that is the sufficient condition. Now it is very easy algebraic manipulation, and you can see that we can write this alpha d as log of 1 plus 1 by gamma. It is very simple. Now you know that the expression for alpha, what was that? Alpha was same as AP exponential minus BP by E. This we have already derived, and you know E equal to V by D. Now for breakdown, what we will say? This V is the breakdown voltage. So if that is the case, then we are putting that over here. So it is AP, and this D is getting joined over there. So APD exponential minus BPD by VB, because we are replacing this E as the VB by D. So that is the standard form of for the electric field. So we are just putting that, and that is coming as log of 1 plus 1 by gamma. So exponential BPD by VB, that is coming as, you can just you can change the sides, and you can easily find out that it is APD divided by log of 1 plus 1 by gamma. So what we are getting VV, so you can just take the ratio, you can easily find out that this VV is equal to, you have to take log of both the side, then BPD, this one, divided by log of APD by log of 1 plus 1 by gamma. So this is the the breakdown voltage that you will require for a gas at pressure P, and the properties of the gas that is already contained within this gamma and the coefficient A and B. Okay. So this gives us a criteria for breakdown to happen. Now you are seeing the condition that VB is equal to BPD by log of APD by log of 1 plus 1 by gamma, as we are seeing here. So this condition for breakdown which we have just reached, this is called the Paschen breakdown condition. Now looking at this condition, as a physicist, you will see that it is having some specialty in the structure. So what is the specialty? I hope that some of you have already guessed that the controlling parameter, what are they? They are the pressure, as we have already seen during the derivation of the this Townsend fast ionization coefficient, that depending on the pressure the free path will vary, so it will affect your this breakdown. And the other thing is that how long it has to go, so the discharge gap, so that also will matter. But the interesting thing is that here what you are seeing, the functional relationship of VB is coming as a function of this product of this P and D, that is pressure and the discharge gap. So the breakdown voltage is not a function of P or D alone. So it is a function of the product P and D. So that is what is very, very interesting. The dependence of VB as a function of PD is plotted over here, and what you are seeing, this is giving a relationship of this kind. So this is VB as a function of PD, and you are seeing that at certain PD you are getting a minimum in the breakdown voltage. So how to find out the minimum? You are master in doing that. So you just take a derivative of VB as a function of PD, and you will equate it to 0, and that will give you the condition for PD minimum. And after doing this, the this derivative is very easy, and you can just find out straight away from here that PD minimum is E by A log of 1 by 1 plus 1 by gamma. So such a simple relationship you are getting for the minimum breakdown voltage. Now, if you are knowing the value of PD, then you can just go back and put that value of PD over here, and you get the minimum breakdown voltage as 2.718 B by A log of 1 plus 1 by gamma. So, what you are getting now, you are able to find a relationship between the breakdown voltage and the product of pressure and the discharge gap, and you are now able to tell what will be the minimum value of the product P and D, and you are able to tell what may be the possible minimum breakdown voltage for a particular gas at a particular pressure. So, what you are seeing that this PD mean is having some value, but what you are seeing here that VB mean is independent of pressure almost. See, B by A log of 1 plus 1 by gamma, it is not having any pressure component of here. Okay. So, this gamma is a function of the property of the gas, and the minimum breakdown voltage, whatever you are getting over here, this is having the expression. And PD mean is again this having this functional relationship E by A log of 1 plus 1 by gamma. Here this is the product of pressure and the discharge gap. So, if you are having that higher pressure system, high pressure system, then you can break a very small gap for that given this for that minimum PD whatever you are getting. So, that is requiring a very smaller discharge gap. But if your P is low, then you can increase D. So, that is how you can break a larger gap at lower pressure applying the same external voltage. Okay. So, with this I conclude this part of this pass chain breakdown condition, and then I explain why the nature of the pass chain breakdown curve is like this. So, we see that this is the PD min and this is the minimum breakdown voltage. So, on either side of this PD min, the curve is increasing. So, here also it is increasing, in this side also increasing. So, on the left hand side of this PD min, why it is increasing? Because you are reducing the PD. So, for a given discharge gap, basically you are reducing the pressure. If you are reducing the pressure, there are too few collisions which are happening to cause the ionization. So, because of that, your this breakdown voltage is now increasing. So, that if you give higher voltage, then you will be having higher electric field. So, the electron will be able to travel a longer distance to make the breakdown to happen. Then why on the right side of the PD min, the breakdown voltage is increasing? This is because PD is increasing for a given gap, means that pressure is increasing. When pressure is increasing, the mean free path is decreasing. So, for a given this voltage, the free time for which it is getting accelerated, that is getting reduced. So, because it is now getting accelerated for shorter amount of time before it get enough energy, it is colliding. So, you need to increase the electric field, in other way the background voltage, so that you can impart higher energy in a shorter time. Okay, so that the force is more, so you can impart higher energy in a shorter time before it collides with the other particles. So, that is how the breakdown voltage is increasing on either side of the PD min. Okay. So, this is the explanation of the pass chain breakdown curve, and what we do now, we go to the different discharge regimes actually in in plasma. Okay. So, this is a discharge tube in which I have one anode and one cathode. Okay. You know that your cathode basically emits the electrons and they reach the anode. Okay. Now, in this what we have done actually, we have filled some gas at certain pressure, and we are applying some bias between these two electrodes. So, because of the bias, the electrons which are there initially, the stray electrons which has been produced, maybe due to ionizing radiation, or due to some high energy particles like cosmic ray, or maybe due to the number particles, few number of particles which are there, always at very high energy in any gas, especially corresponding to the Boltzmann tail region. So, somehow we are getting some electrons which will be participating in the acceleration process, but they are not very large in number, very insignificant. So, initially you will be having some current, but that current may increase as you increase the the potential, but a time will come when all of them are collected. So, after that time, the number of charged particles which are passing to the this anode per unit time is constant. So, no more increase in current, because current is that Q by T, now amount of charge that is passing per unit time. So, that is now fixed because all of them are getting collected. So, you will get a plateau. So, this is exactly what I have plotted over here. When the applied voltage is very low, so in this direction we are applying the voltage, and in y direction what we are doing, we are recording the current that is passing through the discharge tube. So, when the applied voltage is very low, extremely weak, 10 to the minus 16 ampere, because the kind of electrons available is that low. So, some random current pulses are observed. Now, if there are some external ionizing sources like light, nuclear radiation, or cosmic ray, or something which can ionize, then that depending on the kind of radiation it is having, so it is having some constant value of current. Why is this constant? Because as you are increasing the potential, that is having no effect, because it is able to collect all the electrons whichever was present there. So, still the current is extremely low, you can see where it is happening, and this plateau region is similar to the Geiger region in GM counter. Now, as you increase the potential further, so up to this you are seeing that the plateau region is there, then when you increase the voltage further, you see there is an exponential rise in the current. Okay. So, this region is basically the Townsend region, which we have just discussed, that electrons are getting multiplied as they are moving in the field. So, they are producing more and more number of electrons, and avalanche is taking place. So, that is causing the breakdown, and the current suddenly shoots up like this. And that is the basically corresponding to the breakdown region, and then the current increases by several orders of magnitude. You see here, there it is 10 to the minus 12, and here it is 10 to the minus 5. So, 6 order of magnitude increase in the current because of the breakdown, Townsend breakdown that has been happened over there. Now, if the current is allowed to increase further, then voltage start dropping, and finally it reaches a minima, then starts again. So, this region what you are seeing here, this is called the glow discharge region, and before the glow start, this region where your when the current is increasing, the voltage is falling. So, this region is called the corona region. Okay. So, after this, actually this glow discharge region, which ends over here, and it consists of different regions like subnormal glow, normal glow, abnormal glow, and after that, if you increase the current further, what you are seeing that the current is quite high, around 1 ampere or more, then your voltage is reducing as you are increasing the current. So, this negative Vi region is basically correspond to the arc discharge, for which we have discussed a lot in the previous lectures, that the arc plasma devices, what are their features, how they are operating. Now, glow and arc discharge can be formed inside the same plasma device depending on the operating zones of the Vi characteristics. Basically, that glow discharge usually appear at a very low pressure, like say less than 100 torr or so. But as you keep on increasing the pressure in the same device, same discharge configuration, as you increase the pressure, then that glow gradually shifts to the arc discharge mode. Okay, so this is the this arc discharge region, and lots of devices are operating both in glow as well as in arc. Okay, and some of the devices are operating in the corona modes as well. So now I'll tell you the features of the glow discharge, because we have learned a lot about the arc discharge. Now something about the glow discharge. So what is glow discharge? You are keeping the gas inside the tube at quite low pressure, say around 10 to the minus 6 torr or so, and then as you are this increasing the pressure, or then increasing the discharge voltage, so different kinds of phenomena they are happening. But the kind of aspects, physical aspects that we'll be describing, that are very typical to the glow discharges. Okay, so typically the plasma parameters, electron density is of the order of say 10 to the power 16 per meter cube, and neutral density of the order 10 to the power 19 per meter cube. So the ionization is quite high, and electron temperature can range from 1 to 3 electron volt, and at the same time the heavy species temperature is of the order of few hundreds of Kelvin, and you can easily touch it by hand. So like the tube light that is glowing in your room, that you can touch by your hand and it will not burn you a lot. You can just feel a bit hot. So there you can understand the temperature may not be more than say 50 degrees, 60 degrees centigrade, because otherwise you cannot touch that. It would be so hot. But if you are able to touch it by hand, then its temperature must be around that. But you see the electron temperature, that is 1 to 3 eV. 1 electron volt is how much? It is 11,600 Kelvin. So when I am saying that it is 3 eV, so 3 eV, it is more than 33,000 Kelvin. Whereas this heavy species temperature, it is only few hundreds Kelvin. So there is a very huge difference in the temperature of the electrons and the heavy species. So that is a true kind of this non-equilibrium plasma that you are forming over here. So typical current in glow discharge, it is of the order of few milliamperes, and electrons undergo fewer collisions with neutrals due to lower density of gas, and hence can gain huge kinetic energy. So that is how the energy of the electrons are so high, and it can support various kinds of waves and instabilities inside this because of initial perturbation in the electromagnetic field distribution. Basically it can support number of electrostatic waves there as well. So it is very rich in waves and instabilities, this kind of glow discharge plasma. And as you reach higher and higher pressure, the instability gradually reduces, and there are different kind of instability starts. So you are shifting from one region to the other region. Now in glow discharge, because very low velocity of electrons, a sheath of electron is formed just adjacent to the cathode. So this layer looks like dark, and this region is called the Astron dark phase. Similarly, you will see that after that there is a glow region. Why it happens? Because as the electron cross this region, some of them recombine with the ions. They are heading towards the cathode, and they recombine with them, and the energy released in that process comes out that photon. Okay, so when these photons are coming out from that region, you see that a bright region develops after the dark space adjacent to the cathode. Okay, so this region is called the cathode glow layer. Similarly, you will see that after this there will be a dark layer, and that is why. Why? Because electrons gain more and more energy, and due to higher velocity, the probability of recombination with the ions which are heading towards the cathode reduces. So this glow gradually reduces to form a relatively darker space, and that is called relatively dark space, that is called Crookes dark space. So similarly, as you proceed, there will be dark, bright bands, and I will explain those things in the next class. So I stop here and meet you in the next class. Okay, thank you.